All right, dudes, right? What are you giggling at?
Sure. Okay.
Let's make sure the answers make sense.
Well, I mean,
That's so nice.
no. I know the answers make sense. I meant make sense to you.
Oh, gotcha.
Like, I know that this is good. Okay. Can we read the problem?
Yes. The cart is propelled up a hill by a compressed spring as shown. It rises vertically 1.4 meters. How fast is the cart moving at the top of the hill? If the cart loses 25% of its energy before it gets to the top of the hill, will it still make it all the way up?
Well, let's just deal with the first part first. Okay. So there's a spring. It's at the bottom. It pushes the cart forward. Then that cart goes up a hill and it gets to the top. And it wants to know how fast is the cart moving. All right. Step one, draw the bar charts. Right? If you can draw some bar charts that make sense, you're good to go. So where's all your energy in the initial condition?
Elastic energy.
It's all elastic energy, right?
Mm-hmm.
Perfect. And did you solve for how much?
Yes. We did the equation, which is 1/2 k times x squared. And I forgot. Well, we figured it out, and it was 8 joules. It was all 8 joules.
Absolutely. So they used 1/2 kx squared. I think in the sheet it says d, but it means x. I don't know what the problem is. I'll have to work on that. So 1/2 kx squared, you got 8 joules. So you have 8 joules of elastic energy. That sounds pretty good. All right. And then what happens after that?
When it goes up the hill.
Goes up the hill. So what is the energy situation when we look at it again?
Well, it gains height, so it gains gravitational energy. But it's still moving. But it still is moving at the top. So you've had a kinetic energy. So it puts 7.
Oh, so this is great. So just the words that he used are perfect. So it went up a hill and it gained some height. Therefore, it gained the gravitational energy. Also, it's still moving. Therefore, it has some kinetic energy. Okay? Now, we don't know how much of each until we do a little bit of plug and chug work. Okay? So what did you solve for first?
We solved for the kinetic energy.
So we didn't because
Or the gravitational first?
yeah, because
Gravitational first.
you know the M, the G, and the H, right? Okay, so you plugged and chugged M times G times H, and what did you get?
Gravitational energy was 7 joules.
Okay, this is the moment of truth. You ready? This is the moment of truth. What's your total energy?
8.
8. And then you look at it in the final condition, your total is still 8, and if 7 of it is gravitational, how much of it is kinetic?
1.
Okay, you guys see where we are in that? So you have to have the same amount of energy total, and then in the first part, there's no energy loss, so it looks pretty good. Okay, so you have 1 joule of kinetic energy, and then what'd you do from there?
We figured out the velocity or the speed. We had to just do the kinetic energy formula and plug in with the 1 joule that we knew, and then find the v, which was 2 meters per second, and that was the speed that it was going at the top of the range.
Absolutely. Okay. So 1/2 mv squared, you knew the kinetic energy value, you saw for the speed, 2 meters per second. That looks great. All right? All right, now, let's examine the second part. Read the second part again. If what?
If the cart loses 25% of its energy before it gets to the top of the hill, will it still make it all the way up?
Okay, so catch this. Perfect. Now, how many blocks do you have in your bar on the left side?
8.
There's 8, right? And so you're going to lose 25% of that to thermal. If you have 8 and you lose 25% of that, how many is that?
2.
That's 2. Good. Perfect. Now, here's the question. Is it going to make it up the hill or not? Yes, what do you think?
I don't think it would, because if it has 7 gravitational, then you would, and it has 2 thermal, then that's already 9, so it wouldn't be able to make it to the top.
Okay? So Michaela said, look, I know that when it gets up to the top of the hill, it's going to need 7 joules of gravitational energy. But if you only have 8 and you lost 2 to thermal, are you going to have 7 to be able to get up there? No, not at all. And she's 100% correct. So that's exactly the right answer and the right reasoning. is that you're going to need 7 joules of gravitational energy, but if you lose 2 out of 8, you only have 6 left. Therefore, I can't get a psi. Sound good? Perfect. All right, we got one more? No, you just leave it there. All right, nice. That was great. All right. Whoa. Oh, I love this one. So this is number 12. Okay? This is number 12. It's about an elevator.
Am I not supposed to do that?
Oh, it's fine.
Oh, okay.
Don't let it slide off following the toes.
Of course not. I remember.
I know you would be the person to do that.
All right, what's it say?
It says a 5,000 kg elevator initially is at rest and raced upward by a motor 80 meters and ends at rest. What is the change in gravitational energy of the car and how much work has been done by the motor?
So let's look at this one because I find it interesting. Is your car moving to start?
No,
No, so there's no kinetic energy. Is it on the ground?
at the beginning.
Yeah, so there's no gravitational energy and there's no springs or anything, true? So look at her bar chart on the left. What do you notice about the energy in the bar chart on the left?
Nothing.
There's no energy there, right? But on the right side, what kind of energy do we have in our final situation?
We have gravitational energy.
It's all gravitational, right? So you started with 0 gravitational and now you have some gravitational. And how much?
We have 4 million joules.
Good, 4 million joules. Okay, and how'd you calculate that?
We plugged in the mass, the gravity, and the height.
Good. So the mass, the gravitational field strength, and the height. That looks pretty good. You got 4 million, right? So that's the change in gravitational energy. And then the question is, how much work was done by the motor? And how much?
4 million joules.
It's 4 million joules, that's right. So the work is the transfer of energy into or out of the system. Okay? Work is the transfer of energy into or out of the system. Is that cool? So if you started with 0 energy and now you have 4 million, where did it come from? Had to come from the motor, right? So the motor put those 4 million joules of energy into the system. How's that seem? Cool? All right. So we're going to adjourn back to the front of the room for a couple minutes, and then we're going to head back. So come to the front. I want to point out a couple things for you. All right. I'm going to draw a couple pictures. All right, so let me just point out a couple things so that they make some sense for you, okay? So this was our original spring lab. Do you remember this, the original spring lab? All right, so this is our original spring lab. If you stretch a spring out, you can store energy in it. Where is the energy on this graph? Where is the energy? The x is the stretch distance. The F is the force. Where's the energy? The slope is the spring constant. I like it. You guys are good. Good. Remember, the energy is the area. Remember that? All right. So energy is the area. Now, what we're going to do is we're going to try to figure out what the units for the energy are. Okay? So this is our moment. We're going to try to figure out the units of the energy are. So what do we measure distances in? Meters is correct. And what do we measure forces in? Newtons, right? And so if I go to calculate the area here, it's a triangle, 1/2 the base times the height. So then what are the units? Well, our height units are newtons, our base units are meters. So I multiply that, I get units of Newton meters. Is that cool? So you get units of newtons and meters. Now, this is the unit of energy right here. We're going to talk about the abbreviated thing in a second. But let's look at our energy equations, because I actually really like this. So our elastic energy equation, which we got from here, was 1/2 little k x squared. Okay? So let's talk about what the units are for this. K is the slope, so it's newtons per meter, and then times meters squared. Okay? And if that's our case, we have meters squared over meters. Somehow this magically disappears, and we end up with Newton meters. So that's what we expected from this. That's what we got. Everybody's a winner. Is that cool? What about the gravitational energy? How do you calculate the gravitational energy? All right, M times G times H. Oh, fumble. Remember that? All right, so what's the unit of mass? Kilograms. What's our G value? Check the, it's 10 what? So it's newtons per kilogram. And then height's measured in meters. And if you have kilograms divided by kilograms, that's like x divided by x. It magically disappears. And what are we left with? Newton meters. Is that cool? If you want to find the kinetic energy, it's 1/2 mv squared. Now, this one's a little complicated, so try to focus on this because it's really interesting. So, what are the units of mass? It's kilograms, correct? And what about speed? What do we measure speed in? It's meters per second, but it's squared. And so I want to know, do you think that that is also Newton meters? Do you think that's also Newton meters? Well, I guess the question we have to ask is, what's a Newton? What's a Newton? Well, if we remember back to when we studied force, we know that if you want to calculate the acceleration of an object, you can take the force, the unbalanced force, and divide by the mass. Does that seem vaguely familiar to you? Vaguely familiar. All right, so what that means that if I multiply, I end up with force is equal to the mass times the acceleration. See that? This is very physicsy. People always talk about force equals mass times acceleration. This is what it means. Like, if you have an unbalanced force on an object, it's going to accelerate. That's what that means. Now, here's the thing though. We measure forces in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. Now, I know what you're thinking. You're like, no, acceleration, we've always measured it in meters per second, right? Because an acceleration tells you how much a velocity is changing. So, what this means is that for every 1 second, my velocity changes by this much. But look what happens mathematically. I have meters per second divided by seconds. You with me on that? Now, I'm going to make this into a fraction. If I divide by a fraction, what's the procedure I go to simplifying that? Multiply by the reciprocal. And so this ends up being meters per second times 1 over seconds, and seconds times seconds is. So that's how I got my unit for acceleration. Is that cool? All right. happening in the world? What is going on? Just bear with me for another like 4 or 5 minutes. This will be a short thing. So let's look at this here. This is a Newton. It's kilograms times meters over second squared. And look what I have here. You see I have kilograms times meters squared over second squared. So you see I have second squared on the bottom because I had to square it, and on the top I have meters and then times meters, which would give me meters squared. But if you're paying attention at home, kilograms times meters over second squared is the same as a Newton. And so I end up with Newton meters. See, 1 Newton is the force required to take a 1 kilogram object and give it an acceleration of 1 meter per second per second. It's the force required to take a 1 kilogram object and accelerate it with 1 meter per second per second. That's a Newton. And so in all of our energy equations here, okay, in all of our energy equations, we end up with this unit, Newton meters. It's how much force was applied over how much distance. That's our energy concept, okay? And you can store it in a spring, or you can store it in a gravitational field, or you can see it in the motion of the object. They're all the same. And for simplicity, although I'm not sure it's any more simple, they took this idea of a Newton meter and they called it a joule. And it's named after a famous physicist. I think his name was like Robert Joule or something like that. I have no idea. So joules is the name we give, or is the unit we give to energy. But really, you need to apply a force, and that force needs to last over some distance. That's how we're going to get energy. And you can either store it in a spring, or you can store it in a gravitational field, or it can be in the motion of an object, and that's how we notice it. So when you write your energies, we're going to write it in units of Newton meters or in units of joules, and that'll make some sense moving forward.
I think it's stuff like electricity stuff too. Like they say like this, what's the name, has 1,000 joules or whatever.
So you might get electricity stuff in terms of joules. Normally when we measure electricity stuff, it's either in volts,
What?
watts, we're going to talk about watts, amps, and ohms. Those are the units that we usually see in electricity. Now, you can talk about electrical energy, and if you're specifically talking about electrical energy, you would see it in joules, because that's whatever energy. All right, how's that seem? Is that all right? So I wanted to point it out, now that we've had experience with these equations, when you calculate it, it's definitely going to be in terms of joules. One last thing. We talked about this a little bit on one of the boards. If you want to calculate the thermal energy, you're going to take the frictional force times the slide distance. Okay? Here, I'll put a reference. So if you want to figure out how much thermal energy is generated, you can take the frictional force times the slide distance. I don't know if we're going to see that or not. What's interesting to me, though, is if it's a frictional force, it's measured in newtons, and distance is measured in meters, so it still makes sense. All right, that's enough of that. All right, so what are we doing today? Well, it's going to be today and tomorrow. So one of the things I want you to do, okay, is I want you to be able to get good practice, and then when it comes to assessing, be ready for an assessment. That's like my whole goal, right? I don't want anyone to have to assess if they don't feel like they're ready, but it's not a big deal, because even if you're not, we're going to have a reassessment anyway. I know we assessed last week. I'm still holding on to those assessments. I haven't decided what I want to do with them. I'm in the middle of formulating a plan. The issue is that with some kids at home and some kids here, it's actually a little bit more logistically challenging than I know how to deal with it. Okay? So we're going to keep moving forward. Okay, we're going to keep moving forward, and here's what I'm going to do. In a moment, I'm going to give you Work and Energy Assessment 2A. Not to take right now. Okay? We're going to use it as a practice. So you're going to go back to your groups, you're going to work in your group, and you're going to complete this thing. Okay? You're just going to work through it. We're going to see, can we generate some answers to these? I'm going to come around, fill in some holes if you have questions. This is a great moment for you guys to work with each other and see like, yes, this is something I don't understand, or this is something I totally understand and I can help somebody else. It's also a way for you to be really honest with yourself about what you know and what you don't know. Does that make sense? So that's what we're going to do right now. So I have this for you, okay? All right. You're going to complete this and you are going to turn it in to me. There you are. You're so welcome. All right. You're going to complete this thing and you're going to turn it in.
Thank you.
We're also going to prepare some whiteboards for it in a little bit to make sure that we're all on board. All right, we're going to complete some whiteboards to make sure that we're all on board. And so that anybody who's playing along at home, sorry, anybody who's playing along at home can also get a sense of how to do some things that they either do not know or do know how to do. This should only take a couple minutes to complete. It's actually not very long. We don't have to do number 9. We will do number 9 later in the week. You're so welcome. Okay? We don't have to do 9. We're going to do 9 later in the week. All right, so here's what I want you to do. All right, migrate yourselves back to your stations. All right. All right, and I want you to put your pencil to your paper. Work with the people. Okay? Work with the people. If you have some questions, you can ask me. I'm happy to help. All right.